So people are still filtering in, but in the interest of time, let's go ahead and get started. I'll keep monitoring and letting people in as they continue to trickle in here. Welcome back to this unexpectedly online third day of W285. Um, we'll make this work. We're using Zoom here today. I'm recording the lecture as well, and it'll be posted on the class YouTube list. So if you feel like you missed something, as with all the lectures, you can always go back and review the video, and I think it's going to turn out okay. Where we left off on Wednesday is I was just talking briefly about debugging, but I think it's also really important to talk about the whole point of using programming as part of the engineering problem-solving process. And we're going to kind of sort of step through an abstracted version of that process with something of a toy example. Let me mention before I begin with this that if you do have any questions, if you'd like to stop me today, probably the best way to do it would just be to post a question in the chat, and I will stop and relay it, repeat it, and then we can try to answer any questions that we may have. As I record this, I'm only recording my own audio video, so don't worry about being captured on the recording. That won't be the case. I'll repeat any questions that you have along the way. And I have this slide up here to talk about problem solving, because this is a problem solving course. Almost all of your engineering courses are going to be problem solving courses. So I don't want you to think of programming and problem solving as being two kind of separate things. They are one and the same. They are directly related. We are using a particular tool, the computer and programming for a computer, in the service of performing some important problem solving. And it's a multi-step process. And from my perspective as the instructor of this course, I care so much more about seeing you go through this process to solve a problem than I care about, syntax. I know we get stuck with syntax. We get errors, and we get compiler issues and runtime errors, and we have to spend a lot of time kind of debugging those along the way. And that's what I talked about on Wednesday. A good chunk of your time will be spent on what I list as the final part here of writing the code, testing, and the debugging. But in an ideal scenario, all of that writing code, testing, and debugging is in service of a problem that you're trying to solve. And being able to document, being able to demonstrate, being able to show that you're able to think through a problem that you're trying to solve is way more important. You will be able to figure out the syntax. Maybe not today, but eventually you'll be able to sort out the syntax for the problems you're trying to solve. You will get better at using the tools to help you write the programs and test the programs that you need to write. But this process of understanding what it is I'm trying to do and breaking it down, that's what really matters. That's what allows you to be an engineer. That's what allows you to create and to build things and really use programming in service of some larger goal here. And it is a multi-step process. That first step is really critical, the so-called problem specification stage, answering the question of what is the problem I am trying to solve. Oftentimes in this classroom environment, the specification is given to you, right? I provide you a README file for each of the lab components, and the goal of that README file is to kind of try to provide you with some version of that specification. Now, that doesn't necessarily entirely solve that first stage for you, because while I've written it, I'm trying to explain what I think the problem is all about, your task then still becomes, well, can I interpret it? Can I understand what the instructor wrote, what he meant? Can I kind of internally translate that into something that's actionable for me? Or do I have further questions at that point? Later on, there is no homework assignment, right? It's really more about what is the problem I'm trying to solve. Can I understand specifically my problem in terms of, from the programming perspective, what is the input to the problem? What is the data that's coming in? Similarly, correspondingly, what is the output of my solution going to be? What do I expect the output to be? Take some input, do some work with it, generate some output. That is something we have to really decide, early on, before we touch any code. All of this happens before we touch any code. What is my input? What is my output? Now, later, as you start to write more mature programs or programs that are in service of some other non-homework assignment, non-lab goal, we have those other considerations beyond just input-output functional relationship, which are the other constraints of the system. How much time does this code need to be able to run in? How fast does it need to be? We don't worry so much about speed this semester. Let's worry about functional correctness. But eventually that is a big consideration. How accurate does it need to be? It's not always as simple as saying 100% accurate is all that we need. Sometimes there's trade-offs that we can manage here. That all goes into that problem specification phase. What are the functional and maybe some of the non-functional requirements of the system? We really need to spend a lot of time in the general case, figuring that out before we worry at all about any code. That's step one. That's the problem specification stage. Step two, I call it just the problem analysis stage. There's a lot of different terminology you'll read for this part of the problem solving process. Just how do I turn the problem into something more manageable? How do I take what could be a very high level specification and a big picture goal I have, and how do I then break it down into more manageable sub-steps? Specifically, when we're writing programs, that tends to involve breaking a problem into sub-problems, and then oftentimes it has to do with extracting the essential variables and their relationships. This is usually specific to programming, but it's critical in a lot of problem solving as well. What are the things I'm going to need to have to keep track of the intermediate steps of those sub-problems? I've used the term a couple times. That's also referred to as problem abstraction. How do I take this big problem and how do I break it down into something manageable at the end of the day? That's analysis of the problem. Again, while some of this analysis that we do is then going to correspond to some code we're ultimately going to write, and that abstraction may then lead to specific code that we are going to write, it is separate and hopefully ideally before we even get started with any programming. Step three, the term you will see in other contexts is algorithm or algorithm design, which is now that I have a better understanding of the specification and have maybe broken down the major tasks into what variables I'll need to create and the subcomponents of the steps along the way, now I go even further and say, what are the actual series of actions that when taken together get me to a solution to the problem? And when someone refers to an algorithm, and that's a whole term of art in computer science, there's a lot of formalisms associated with it. As EE students, you may not get too much more in depth in algorithm design beyond what you will learn this semester. In practice, what that really means is just what is the math I need to get from my input to the essential variables to eventually to my output. We keep the math pretty reasonable this semester. Depending on the problem you're trying to solve, it may become more advanced as you learn more of that math as a EE student. Once you have those three phases, an understanding of the specification, my input output, a breakdown of the problem into a series of variables and sub-steps that get you to that output, that's the analysis, and then what math is required to actually do those transformations from input to those essential variables to the output, the algorithm. Once you have a feeling for that, an intuition for that, frankly, once you've journaled that down, once you've written that down somewhere, then let's worry about coding. Then let's worry about syntax, worry about debugging and things like that. Otherwise, if your approach to problem solving this semester and beyond is, well, I have a problem I have to solve, let's just start writing some code. When things work, you're fine, obviously. But when things don't work, it's very hard to kind of inspect what you're trying to do and understand where things didn't work out. And your debugging process is going to involve a lot more trial and error and starting over than if you actually had a plan. If you've actually thought about the problem first, abstracted some of the difficulty of solving that problem, and then worried about the code. We'll work on a pretty high level version of that together. My plan for this originally was that we were going to do this in class, take a few minutes and see how far you can get in teams of 2 to 3. We could try that on Zoom. I don't think it's really worth the effort. So what I'll do instead, I'll kind of just walk you through my thought process for some of the problem solving for this particular problem. And then we'll dive into some of the lab related code as well. And while I won't do the lab for you, I'll talk you through my thought process for how I would go about some of the challenging parts of that very first lab. I know some of the teams have it all figured out already, and that's wonderful. But I know for quite a few of you, that was kind of a sticking point in this first lab, and intentionally so. So here is a particular problem. It's a synthetic academic one, so be it. The problem is, how do I determine someone's age in seconds? Okay, well, we have to think about that, right? My first step should not be, let me open up Replit or my favorite IDE development environment and start writing up some code for that. The process should be, okay, how do I break this down? What is the input? What is the output? What are the individual steps along the way? Okay, so the problem is how to determine someone's age in seconds. For me, the most appropriate tool in the problem-solving process, again, this is kind of my bias, and you don't have to do things exactly how I do it, but for me, the most important tool is pencil and paper, and that's kind of old school. I don't have this. It's not going to record me writing down things on pencil and paper. Use a tablet, use a text editor. When I want to make quick and dirty notes, there are a million tools that allow you to do that as well. One you could just use as a markdown editor or a Google Doc editor or Microsoft Word, whatever your tool of choice is. Markdown for me is simple enough that I can just quickly jot down some notes. And they're really for my own internal consumption, and then I can take that and use that as my starting point for writing some code for a problem. So I have here just a Markdown editor as Visual Studio Code. It's perfectly fine for this purpose. The goal, determine someone's age in seconds. Okay, that's our goal. That's where we're starting with, our initial goal here. First step of the problem-solving process is understanding the specification. Okay, and again, I'm doing this a little formally today. It's not required that you be as formal as this when you do it, but so be it. This is how I am doing it today. So something like, you can call problem specification. This is a bit formal for it, but that's fine. And what I mentioned for the problem specification, what we really care about again are what is the inputs, what are the outputs, what are the constraints in terms of runtime and accuracy. For me, for this, I care about the inputs. Well, the inputs would have to be, it depends, but I would say, input would have to be, well, it depends on how we do it. It could just be someone's age in years. That's one possibility. Could also be potentially today's date, someone's birthdays is another way we could do it, right? So you could do it where the input is just 25 years, or it could be, well, today is August 25th, 2023, and here's someone's birthday, and that could be how we could determine someone's age in years. Also, outputs then would be someone's age in seconds. As part of this consideration, there's the constraints. Accuracy is kind of given as part of the specification. Perhaps, round to the nearest second based on today's date. So it would really be based on today's date. So it's really rounded to the nearest, say, day. I guess we get to decide that, right? So this is part of the problem specification. So it's rounded to the nearest day based on today's date, because otherwise the answer would be changing every single second as we work on it. So that's kind of step one, right? It's one version of thinking about step one here, where, okay, the specification is given to you as just a single sentence. How to determine someone's age in seconds. Okay, what does that mean? What is my input actually going to be? What is my output going to be? Let me reiterate here, and I think this is important. You may be looking at that and saying, well, I have no idea how to code that. That's okay. We haven't learned it yet. We haven't done any programming yet, right? We're just kind of figuring things out as we go here. Eventually, how to translate that, gathering inputs, generating outputs into code, is going to be the relatively straightforward part. We still have to figure out how we're breaking down the problem here. So we'll worry about code when we get better at writing code. It'll be something we kind of scaffold as we go here. Step one, breaking down the problem into input and output, some aspect of constraints otherwise. Step two, we were calling the problem analysis. which was breaking the problem into separate subproblems and extracting the so-called essential variables and their relationship. So I would think of really what's critical here are what are the essential variables here. Again, a variable is going to be a way in which we store some intermediate value that we care about as we break down the problem. There is not at all in any way, shape, or form one correct way to do this breaking down, determining what variables are needed, but it is always better to think about that versus not to think about that. So while there's not one correct result, really the incorrect path is to not think about it at all. So here we have to think about what variables are valid for us. And there is no right answer. There's no singular right answer. But any answer that you've thought about is better than no answer at all for this, if that makes sense. So some possible variables that may make sense, like how about like age in, it doesn't sound good, right? How about instead of age in, because that looks bad, num years. That's something we can calculate first. What's the number of years that someone has been alive? And perhaps from there we go from num years to num months, to num days, to num hours, to num, well, you see where I'm going with this here. Maybe we don't need all of these, but they're here. If we decide we don't need them, that's still not a problem to worry about, to num seconds. So given an input of either someone's age just in years or perhaps today's date and then someone's birthday, and we're eventually outputting someone's age in seconds, maybe finally now that num seconds is the actual output value that we care about there. That's what we're actually trying to calculate here. Some version of that is critical. Otherwise, if you start just diving into the code, you're just randomly coming up with ideas and not really thinking it through logically from beginning to end here. What is the algorithm? What are the series of steps? What is the math that is required of this? For this, it's really just a breakdown of how do we get from years to seconds, how many steps we actually care about along the way. Well, there's a trade-off involved. When we have more steps, maybe potentially the program is having to do a little bit more calculation and a little bit more work. But here we didn't even mention any runtime constraints we were interested in. The advantage of having more steps is that there's more things to kind of debug when things aren't working, more information you have to be able to look at and say, well, my result's not correct. Let me look at some of the intermediate variables that I broke down and figure out where things are going wrong. Whereas if you try to do it all in one step and your algorithm is just one very long line of code here as implemented, when it works, you're fine. And when it doesn't work, you don't have much to go on in terms of determining where things are wrong. So, I mean, we can keep this at a pretty high level, but it may be something as simple as saying, first we have to calculate how many years old someone is. And it's going to be something along the lines of, how many years old. It's today's year minus birthday year or something like that, right? Determine how many years old someone is going to be given that. From the number of years, we can go from num months. Honestly, we could probably for now skip num months given num years. Num days in a year is going to be given by the number of years someone is old times 365, right? If we want to really try to be precise, when we're worried about leap year, there's all sorts of extra math, and maybe it's 365 and a quarter to take some semblance of a leap day into account. We'll talk about some of the considerations of that very soon here in terms of, okay, what type of variables do we need in C as a programming language? But that shouldn't influence our algorithm design very much, at least in the beginning here. Given a number of days, we can go from there and say, so num hours equals num days times 24. We can go from there, right? Num minutes. I don't know if we need all these intermediate stages, but we have them now. Num hours times 60. And then, as we get to our num seconds equals num minutes times another 60 for 60 seconds in every minute. This is at least some way, shape, or form of breaking down this problem. It doesn't do the code for you. We haven't started any C code. We're not actually going to write any C code for this particular problem. But at the very least, we can look at this when we're starting to write our code. We're starting with a blank file, a blank main.c file, and we can look at this and say, hey, okay, I have an idea of what variables I need to create at the very least, and I can start to look at, as we learn more of the techniques for how to declare variables, how to write expressions for the variables, to do some arithmetic on those variables. We can start to take a look at that and then say, okay, there's kind of a close to one-to-one correspondence, but between my notes for the problem breakdown and the code that I have to write at the end of the day. It's always better to have this notebook, piece of paper, quick sketch, napkin, whatever you want to use for it. It's always better to have this than to have nothing at all and just be starting with a blank .c file and then just hope that, through some sort of muscle memory, you can write code to solve a particular problem here. One part of the problem-solving process I don't mention, but it's more specific to writing code, is what's really critical as programmers, and it's something we'll learn over time, is we really want to get a feel for what existing resources are already available to us from the programming perspective, not from the problem breakdown necessarily. I don't mention it for this example. We haven't really talked about this yet. But when given a problem to solve, and to know that you're going to write a program to solve the problem, and it's a computer programming problem you're solving, we should really look pretty early on in the problem-solving process into what else is already out there. Is this problem already solved in some sense? Another way to think about that from a more technical perspective is there already some software application, some software library that, if it doesn't entirely solve the problem for us, maybe it gets us a decent stretch of the way there, such that we don't necessarily have to start from scratch. From the classroom environment, from an educational programming practices perspective, I will tend to tell you when that's the case. I will say, hey, consider using this application, or please use this existing library to help you solve that problem. But in general, you should be thinking in terms of that as well. What existing things are out there that will make my life easier when it comes time to actually write the program? The problem is you don't know what you don't know. You don't know what libraries are out there. There oftentimes is going to be a library or an application that can really help you in terms of solving the problem, but you have to find it. So you have to know where to look. You have to kind of know also what sort of questions to ask. But that should be part of your problem-solving process as well. Call that maybe step 3.5. If step 4 is the open up the program and get programming, step 3.5 is let's think about that a little bit more. And do we not have to start from scratch? Are there things that are already out there for us? There, by and large, is. Oftentimes we're looking to build upon others' work versus starting from scratch. That doesn't mean that life is simple. Oftentimes, it is very difficult to work with some other application or library. And oftentimes, a big challenge of being a software developer is not writing your own code. It's working with other people's existing code. There's this other library, this other application that does a lot of what we need. But how do we actually use it? And that's something that, I don't know necessarily if I know how to teach that very well. The best thing that I can do is provide you with lots of opportunities this semester to sort of experience that. Experience working with other people's code beyond just doing code entirely on your own here. So for this particular example, determining how old something is or could be in seconds, it turns out there is a utility that's very good at doing something exactly like this. There's more than one utility that's very good at doing something exactly like this. I'm actually going to open up Replit now, and hopefully it's visible on your screen. Again, I'm recording this video, and it should be pretty good resolution. So even if this doesn't look very great for you live, and maybe it's downsampled and things like that, you'll be able to review the video after the fact. This is in our class Replit page. It's under the Lect-01 examples, and you can also take a look at that in parallel. In fact, this is just a copy paste of part 5 of lab number 1, what we call vector graphics fun. Fun is in the eye of the beholder. It's fun for me. It may or may not have been fun for you so far. But this is a good first example of what it means to work with someone else's code. And both the benefit and the drawbacks of doing that. The benefits, I think, are obvious. If I asked you to write an application that does some drawing and saves it as an image file, that's a lot of work. That's many, many weeks of work. You wouldn't be able to get started with that. So the benefits are that it allows you to do this task. That's a pretty big benefit. The drawbacks, I think maybe you're already seeing. It's not that straightforward. Just because this library called libcairo exists, doesn't mean your problems are solved. You still have to break things down. You still have to think about things. And now you have this other additional intellectual hurdle of reading someone else's code, or at the very least their documentation, to understand what it means to actually, work with that particular library. And as a programmer, that will potentially be a big part of your day-to-day task, which is reading other people's code, certainly reading documentation, and understanding, how you can best use this existing library or application to get your job done. We'll talk about libcairo in just a minute here. I want to mention that specifically for the labs, we actually have our markdown file here as well. This is for the lab documentation, for the lab notes. There's both the instructions that are in Canvas, which is really, here's what I want you to submit in Canvas. I posted about that in Discord yesterday. There's then the notes in Replit for each individual lab assignment, which is my attempt to provide you with the problem specification. In addition to that, it is also my attempt to provide you with some hints along the way. These are brief, they are not very long reads. If I provide a link and links inside those markdown files, I really kind of expect you to click on those links. I'm not trying to waste your time with them. These are meant to be read fairly literally. When I write a sentence, I do want you to kind of read and reflect and think about what I'm asking you to do along the way. Your job is not to open up this project, just dive into the code and get started. It's to read and think, add to the notes yourself. If you want to use this same file for your own notes, that's perfectly fine as well. But I want you to look at any links I provided. Anytime in a future lab, if I say, hint, consider doing X, Y, or Z, you don't have to do X, Y, or Z, but I've thought about it, and after having thought about it, I think X, Y, or Z is the way to do it. So consider that as well. We'll look at the libcairo documentation in a minute. It is not an easy example, but it's a pretty representative example. Going back to our determining someone's age in seconds, we can actually take a look at one of our other windows here. So we know that there is both the console and the shell. They're roughly synonymous for our purposes. They provide this Linux environment for you to be able to interface with the remotely accessible computer that is hosting this project, that is running this code once you hit that run button for that particular project. But it can do more than that. It is a full shell. It gives you full command line access to that environment. You can do things like you can do in any Linux style environment. If I want to list the files that are in the current directory, you can do the ls command. There are many, many different of these bash or Linux utilities. We will learn the ones that are most useful. You may not be a Linux expert by the end of the semester, but at least you'll have some reasonable familiarity with it by the end of the semester. For our purposes, for this particular problem that we're hoping to solve here, determining someone's age in seconds, the command that's built in that's kind of helpful is actually called date. Type in date and it tells me today's date in some level of detail, that we have Friday, August 25th, and we also have to the second what the current time is in one particular time zone, the UTC time zone here. For most of these utilities, there are different ways you can find documentation for them. For some of them, there'll be a so-called manual page, and you can type in man and the name of the utility. And if there is a manual page, it'll give you some built-in documentation. I think for this one, there isn't one installed, and so it's not going to find it. There's also going to be online manuals for these. You could Google the date command, and you should find a reasonably good web page. Most, if not all, these utilities would include some semblance of a help option as well. So I would type in date. It depends on the utility. Some would be -H. This one is --help. And when you've done so and pressed enter here, it'll provide you with the so-called help option or the help page for that utility. Again, just like using a third-party library is not a free lunch, you have to understand the library, you have to kind of break it down and kind of go from there. Using these utilities is not free as well, in the sense of there's still some cognitive exploration required here. You'll get better at it. As you see more and more of these, they tend to be written, documentation in general tends to be written in a certain style. It assumes a certain type of familiarity already with the application environment to begin with. So it's not necessarily that easy to start with. Here, I'm looking at this date utility. Again, when I run it by itself, it doesn't give me exactly what I want. I want to know someone's age in seconds. Okay, that's not quite exactly right. But when I look at date and I look at help, and I have to kind of scroll through it here. So it tells you what it does, displays the current time in the given format, or it could also set the system date. So for example, you can say, I want to specify the date. And when I'm specifying the date, I can then also specify it in a particular format here. And there's a lot going on here with regards to what the format could look like. But in one of those formats, it turns out that there's a reference time where you can specify, provide me the date and provide me that date information in terms of the number of seconds that have elapsed. So the number of seconds that have elapsed since January 1st at midnight in 1970. These Linux machines never had a particular so-called Y2K problem, but eventually they'll have a problem. I think it's a year 2034 problem or something like that, where eventually enough seconds will have passed since 1970 that they'll have to worry about values overflowing and things like that. It's mostly a solved problem, but it's something that had to be taken into account. So we have this utility, and it turns out that if we do provide a way of formatting the result of that utility, we get something that actually does tell us the date of something in seconds relative to this particular point in time here, and that's %s. We can specify with that format string that we want to know someone's age since that point in time here. So we can do that. We can type in date, and I believe we just say we want that format string, and now we get somewhat arbitrary looking number. We could probably do the back of the envelope math, but I won't belabor the point. The number of seconds that have passed between now and between 1970, January 1st at midnight, and right now. I could probably keep trying that, and that number should tick up. I don't know, what should be 25, 30 more than what it was before, 20 seconds later, another 2 seconds later. It's keeping a running track of the number of seconds that have elapsed. Going back to that help page, you can also then specify with --date, display the time described by string, by that input, and not what the current now time is. That's also pretty useful, right? In terms of, I want to specify someone's birthday. When were you born? The day you were born. And that would then display, if I also convert it to that format, the number of seconds that have elapsed since that person was born, at least the midnight, presumably, of the time at which that person was born. So that is the date now. If we then also specify using that date command, we can pick an arbitrary birthday. Oh, we'll do September 15th, but I won't use my actual year. Let's do 1989. It would be nice to be born in 1989. That should give us a smaller number of seconds, right? Because the date command takes the current time and calculates that time in seconds since 1970. This is a time that's more recent than 1970, and so it should be a smaller number here. We can actually then do all sorts of manipulations without even writing any C code at all. We can store variables directly in the shell and just manipulate arithmetically in the shell itself without writing any code. So I can create a variable. Let's call it current time in seconds. This is a bit lengthy, but you're the one who has to be able to understand what your own variables mean. Okay, and I can also do I don't want to call it age in second, birth in seconds, and it's that same command. And age in seconds would just be the larger number minus the smallest number, smaller of the two numbers, which is current time in seconds. It's off by a couple of seconds, but that wasn't our spec requirement. Consequently, well, then we have to actually print out that value. We get an answer. It seems reasonable enough. I guess, again, we have to kind of, as you go through the problem solving process, it's important to have little sanity checkpoints every so often, which is to say, are the results that I'm getting, are they meaningful, or are they even close to correct? I don't know. Off the top of my head, I can't tell you whether someone born in September of 1989, are they approximately 1 billion seconds old? That's an interesting thing to think about, right? Approximately 1 billion seconds old. But it's an example of using what is already available, and not in terms of the problem solving process, not really having to write any code at all here, right? I mean, this is code 2. This is, you can call this like a bash shell script or just a series of commands we're executing here. It's not C code, but it's using the utility that already exists, using this functionality that's already there. And so I'm really not reinventing the wheel as a programmer and saying, okay, I'm going to use this very powerful utility. It presumably is pretty well written. You can't always assume that, but in this case, it's a utility that's been around for many, many, many years. They've probably fixed a lot of the bugs that you or I, if we were to build it ourselves, would have had to fix over a period of time. So in terms of a first approximation for how to do that calculation, we still had to kind of think about how we were breaking down the problem. But as part of that problem solving process, what I called step 3.5, we can instead look at that and say, okay, this date utility, and I'm kind of cheating here, right? I know how to use it already. You did not know how to use it already, but this date utility kind of gets us pretty far along the way. So reading that documentation, which I did in 10 seconds, it's perfectly understandable if that takes you minutes and even longer and you have to ask questions, but it's there, and it allows us to really, at least in part, or if not entirely, solve the problem for us. It's a really wonderful thing. We can be so much more productive as engineers if we're not having to start from scratch when it's time to actually solve a problem here. So let's double back to libcairo and that particular problem here. You know, a couple other things, you know, I want to point out. So that green run button does work for this example. It builds the application and actually runs the application. It generates a file that you can preview. The epic vector graphic example, this might be slightly tweaked from the version in the lab, but it's roughly the same thing here. But I call it jokingly the magic run button, but there's actually not magic involved here. They just tend to hide some of those implementation details from you. I want to show a couple of them briefly, but I understand that this is sometimes a pain point in this type of class, that the other things that aren't directly programming, of interfacing with how to build your program, can be a little painful. I want us to have an appreciation for it by the end of the semester. It would take some follow-on classes and more experience to get really comfortable with this aspect of programming. I clicked Show Hidden Files here, and it indicates that there are a number of other files beyond just the .c file and the other things, the markdown file that are there. One of those files is the so-called make file. Make file is another type of script that really tells your system, how do I go about building the application that is specified in part in the source code that you yourself are writing, and in part in existing libraries that may already be installed in that particular system. It has its own fairly esoteric syntax. They tend to, at least in some way, shape, or form, look something like this, where you specify variables like we just did on the command line. In this case, one of the variables is the name of the compiler we're interested in. Other variables will correspond to what compiler options we're providing, and then what linker options we're providing. And in this case, it's also specifying what do I want to call my application at the end of the day. And given that application, what rules do I have to follow? We will eventually gain a little bit more appreciation for makefiles, but for now, it's sufficient to say that that magic run button isn't actually magic. If we look at the .replit, which was another one of those hidden files here, as part of that file, and I'm not going to dive all the way into this file here. This file, amongst other things, is configuring that green button for you. So this file is specifying when I hit the green button, what should I actually do? I should actually compile by running the command make-s, and then actually run the application listed as libcairo test or libcairo test. My Iowan is kind of showing through here. So it's not magic. It's just kind of hidden from you as a user. And separately for the build environment for this particular system, we also then have to specify that for the various packages we want installed as part of the remotely accessible operating system we're accessing here, one of those packages does correspond to that library. So a lot is going on with that green run button. As the instructor, at least to start with, I do that configuration and then kind of pass it on to you. But a big part of that is something that you do have to eventually be pretty aware of as a developer, which is, okay, I know I want to use this utility and this utility and this library and this library. How do I get my application to the point where my code is pretty simple, my .c file is still pretty simple, but how do I get it all to build and connect together and run? And I feel for better or worse as programmers, and it's not a C specific thing, it's true of almost all development environments and languages you may specify, that winds up taking a decent amount of our time. So you may want to also bake that into the problem solving process. Call that step 3.75. Maybe I should have just adjusted the numbers correspondingly. Decide what libraries and packages and utilities may be helpful for you in step 3.5, and then actually get them installed and working and building in your environment. That can take a surprising amount of time. By and large, I try to do that. I try to do that for you this semester. I don't, it's a good thing to be aware of, but it's also can be very frustrating, and I don't necessarily want you to spend a lot of time doing that this semester. But that is part of what's happening kind of under the hood here for this and for several other examples this semester. There's built-in libraries in the system that are kind of assumed to always be there. There's then these optional additional libraries that can be very nice to use. In this case, for vector graphics, there's this library that we're using. Finally, one thing I mentioned on Wednesday was, right, we have this series of translations that happen from source code we specify to these intermediate object files that get linked together to that final executable that is what the processor understands. Those outputs of those intermediate steps are also kind of hidden by default in Replit, but since I selected show hidden files, you can now see them. They're actually there. Clicking on them isn't necessarily that helpful because it's a binary blob, so it's gonna look like junk when opened up in a text editor. There may or may not be a hex editor installed on this system by default. I'm not going to install it right now, but we could look at the ones and zeros if we wanted to. But they're ones and zeros. It's not going to tell us all that much, but it's there. So those binary blobs I was talking about, they don't look like much because arbitrary binary data isn't going to look like much when viewed as text form for reasons we will talk about relatively soon this semester, but they're there. The main.o file is the intermediate object file. The actual final executable is also there, and it's even bigger because it's including all the stuff that's in the library as well. They are there in the system. That file is the one that actually gets executed. The green run button does it, but even if I weren't to use the green run button, I could always just do it myself. And we executed the program again. It ran that file here. So then this gets us to how do we actually do this particular lab? And I do want to mention that if you look at the description, the explanation, what I would like you to do for it. First step, review the source code. Just try to walk through, read my comments, do your best. Based on having no experience for many of you in any C programming to this point in your life, just try to get a feel for what it may be potentially doing. That's all I'm asking you to do so far. in terms of what I would then like you to do, I want you to review the documentation, including the provided examples here. When I open up this tab, I meant specifically, you can look at the samples. There's a tutorial. There's also a reference manual. The tutorial is probably a decent place to start because it gives you examples of some of the functions. And in fact, you should see pretty quickly that the example I provided here, the hello epic vector graphics example, is almost directly lifted from this tutorial here. Tutorials are a great way to learn about a new library that you'd like to be able to use. But I understand that there's still some mental effort required to do that. This is not meant to be trivial. Read through this. Try to get a feel for what can be done here. Your job isn't to become the world's foremost vector graphics expert here. It's to be able to draw something with this library different than what is already being drawn here. Start with something simple and only worry about a complicated demo if you have some time remaining and nothing else to work on. So there isn't that much of a request here. Draw a rainbow, draw a Pikachu, draw something that's just based on circles because there's a nice library and nice function call for drawing circles here. Just adjust the example that is already here. I wouldn't adjust it maybe in a trivial sense, but for example, by default, you may be able to look at this line of code and kind of sort of guess that the end result is going to create a file called hello.png. Well, let's not call it hello.png. Let's call it inclass.png. I don't necessarily have to update this part, but I'm going to say file inclass.png updated. I now run it. File inclass.png updated. It's still the same file here. Have those two things kind of open side by side. Maybe I don't want to call it epic, but now this is my second vector graphics example. This was some text I was wanting to provide in the file. And now we have our second vector graphics example. I don't especially like that it's that kind of light blue color. There's a function, Cairo, set source RGB. We'll talk more about color this semester, but if you've done anything with any sort of looking at applications on the web or just paint of applications, you know, RGB, red, green, and blue are the different colors that we're interested in here. Somewhere in the documentation, in the list of functions here, there should be a function for RGB. It's not showing up directly there. If we look at RGB, there's an example that in this case, it's drawing something in black. It is very likely, although we could guess and explore, that the first value is how much red, the second value is how much blue, the third value is how much green. If instead of having that to be kind of a cyan kind of color, if I want it to be red instead, maybe I would change it to 1.0 in red and 0 for blue and for green. Now we have a second vector graphic example that is not that's not blue, cyan. Now it's kind of red as we go. Other functions that we have here, there's some setting up of variables. We haven't talked about what doubles are yet, but there's a value called XC that's 100.0. I know we're a little low on time, but we'll finish up in just a minute here. There's a value called YC that's 200.0. There's a radius defined of 100. There's an angle. We have to kind of squint and see that we have an angle specified in radians. So if we want to take a value in degrees and then convert it to radians, we calculate it by a value of pi divided by 180. So that's an angle 1 is 45 degrees. Angle 2 is 180 degrees. And at some point here, we are defining an arc at location XC, YC with a radius of 100 going from 45 to 180. If we look at this picture here, from 45 degrees to 180, Now maybe I don't want a yellow arc kind of at that arbitrary location. If instead this one we have as a circle, let's do this one instead. Here's a center circle. Let's make a different one in a different location. That color is kind of a greenish color. Let's make it just a darkish gray color, so relatively low values for R, G, and B. Instead of sending it at that location, we have a canvas of size, should have been listed here, 640 by 480. Let's put it right smack dab in the middle. That'd be 320 by 240. That arc, this case, is of size 10. Let's make it of size 100. And instead of 180 degrees, let's make it 2 pi. Let's make it 360 degrees. If I did that correctly, there should be a big gray circle in the middle. It's awfully black on my screen, but it was meant to be really dark, I guess, gray here. Because I said gray, obviously that's just a little bit low for those. So let's do 0.3, 0.3, 0.3. There we go. Now we get our gray circle in the middle. Draw a rainbow. Draw Pikachu. Just draw something. Just show that you kind of played around with the functions and you did something that is something creative. Go overboard if you're bored between now and the deadline for your lab. It's not a requirement, but that's all I'm really expecting of you for that part 5 of lab number 1. It was not expected that you are an expert on that library. We haven't learned any of this yet. Starting Monday, we're going to start getting involved in the mechanics of C. It may feel slow, at least at first, but do not worry. We will be building upon what we're learning, and what you're going to be able to do with your code is going to be able to continue to grow slowly at first, but at a pretty rapid pace over time. Let's leave things here for today. I very much look forward to seeing everyone in Vancouver again on Monday. And as always, just post questions if you're still working on things, you just have questions in general. I'm very happy, Dayu, the TA, is very happy to help you out. And so we're looking forward to seeing those questions. Otherwise, I also have my office hours. I'll plop into Discord in about 10 minutes here. Feel free to stop by there as well. Otherwise, good luck with finishing up Lab 1, and I will be seeing everybody on Monday.